In this video we're going to remember what a rational number is, what is the definition of a rational number, and how can we show that something is a rational number. So what are the sort of characteristics of that? So first of all, let me remind you of the definition. So if we're saying that a number p is a rational number, or we could say p is rational if and only if, and remember for if and only if we can use our double sided implication arrow there. So p is rational if and only if we can write p as a ratio of two integers a and b, hence the name rational. So it's a ratio of two integers a and b. So let's say a and b are elements of the set of integers. Obviously, for p to be defined, we have the further condition that b cannot be equal to 0. And there's one last condition there, which is that a and b share no common factors other than 1, so it's in simplest form. So a way we could write that is that the highest common factor of a and b is equal to 1. They share no other common factors. So that's the definition of a rational number relating to the ratio of two integers. But you might recall that the way we often recognize rational numbers, because often numbers aren't written in fractional form, that we recognize them by the fact that a rational number, when written in decimal form, will always be a terminating or recurring decimal. So rational numbers are, as decimals, they are always terminating or recurring. Alright, remember those two things. Terminating means finishing or stopping, so at some point the decimal stops, it doesn't keep going. Recurring means that there's a pattern that keeps repeating itself over and over again. So one of the questions we might have then is, how can we show that every number which can be written as a fraction, like this, will be a terminating or recurring decimal in decimal form? Well, it's not too hard to show that, but the thing that we might need to think a little bit more about is, how can we show that every terminating or recurring decimal can always be written as a fraction of two integers, as a ratio of two whole numbers? Alright, well, let's consider a few examples of each of those. So first of all, let's maybe do a couple of examples where we just show that every ratio of two integers can be written as a terminating or recurring decimal. And we'll sort of assume here we're working, tech free, so we don't have our calculator. So we want to show that 3/8 can be written as a terminating or recurring decimal. And to do that, really, we're dividing 3 by 8, aren't we? So we're taking the number 3, we might need a few more decimal places after that, so let's do a short division. So 8 doesn't go into 3, does it? So let's go 8 into 30, and 8 into 30 goes, 3 8s are 24, so we're going to be remainder 6. 8 into 60 goes 7. 7 8s are 56, so we've got a remainder of 4, and 8 into 40 goes 5. So we're showing that indeed 3/8 is equal to 0.375. So there's an example of a rational number or a fraction being a terminating decimal. What about one where it's not a terminating decimal but it's a recurring decimal? So pick something like 6/11, and this time I might use long division. Be a little bit easier as our numbers get a little bit larger. So let's say we're dividing 6 by 11. Obviously 11 doesn't go into 6. So let's say 11 into 60 is 5 times, isn't it? 5 times 11 is 55. So we'll be subtracting 55 from 60. Now, I know we don't do a whole heap of long division, You might not have done much since kind of late primary school, but this is a reminder of how we do it. So 55, we take away the 55 from the 60. 11 won't go into the 5 down here, so drop down the 0. And we're saying 11 into 50 goes 4 times. That's 44. 50 minus 44 is 6. Drop down the 0 there. 11 into 60 goes 5 times. Now you can probably see at this point that we're just going to get a repeating pattern, aren't we? Because we're going to keep getting 50 and 60, so that's going to go on and on. And so our repetend there, the bit that repeats after the decimal place, is just going to keep being 5454. So we could say that 6/11ths is equal to 0.54 recurring. So just a quick reminder down here, maybe let me grab another color. So a couple of notes here. That the 5/4 is called the repetend. And it can also be written now. Remember, sometimes our repetend might only be a single digit, so we just put a dot over the top of it. But even if it's more than one digit, we could write it with alternatively with a dot over the first and last digit in the repetend. So sometimes our repetend might be 3 or 4 digits long. We could put a line across the whole repetend from start to finish, or we could put a dot above the first digit and last digit in the repetend. Okay, so there's some examples of showing that fractions can always be written as terminating or recurring decimals. But like I say, what about the other way around, which is probably a little bit more, sometimes a little bit more involved. So first of all, let's take an example where we're saying 0.26, so it's a terminating decimal, and we want to write that as show clearly that it's a ratio of two whole numbers, two integers that satisfy the conditions that the denominator is not equal to 0, and there's no common factor other than 1. Well, in this case, we could just say 0.26 equals, 26 over 100, which can be simplified, can't it? So what's that going to be? 13 over 50. So there it is. That meets the criteria of a rational number. It's the recurring ones that require a little bit more work. So let's think about 0.28 recurring. So here's one technique that we can use, and there are a couple of different ways or different sort of types of maths that we can use to do this, but for our purposes, let's let n be equal to 0.28 recurring. So let's write a few sort of cases of the repetend, and then we'll just say dot 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 to show that that's what continues. Now what I want to do is multiply that by something which is going to move the decimal place past one repetend. So in this case, I'd say multiplying by 100 makes this 28.282828. Alright, and obviously the 2 8's just continue after that, so even though in the first number I've only shown 3 sort of cases of the repetend, in the second one I've shown 3 again, so there's another 2 8 here, which I guess, is sort of appearing in the second number but not in the first number. But anyway, that's what continues after that. So then what we could do is say, well, okay, let's actually subtract. If I was to number these equations, I'd be saying, let's do equation 2 minus equation 1. So equation 2 minus equation 1. On the left hand side I'll have 100n minus n, and on the right hand side I've got 28.28 recurring minus 0.28 recurring. So everything after the decimal place is going to be subtracted because what's after decimal place is identical, isn't it? So what I'm left with then is 99n is equal to 28, and therefore n equals 28 over 99. Alright, so that was n, which was 0.28 recurring. So what I'm actually saying is 0.28 recurring is 28 over 99, and that can't be simplified any further. Right, let me do one final example where the repetend is slightly different. I'll try and fit it in here. So for this one here, we're going to say 0.523, but we'll just make the 2 and the 3 the repetend. Alright, so I'm going to let's go down on the next line. I'm going to let n be equal to 0.523. Now I could just write it in the same way again, but sometimes it actually helps to kind of see the pattern here. Remember, in this case the 5 is not repeated because the repetend sign there only goes above the 2 and the 3. So it's just the 2 and the 3 that is being repeated. So what I'm going to do first of all is say, let's go just 10 times n, and that'll get the bit after the decimal point. So the part of the number that's after the decimal point will just be the repetend repeating itself. So I don't want any of the sort of non-repetend part on the right hand side of the decimal point. And now if I was to multiply that number by 100, which is the same as multiplying n by 1000, so if I was to go 1000n, that would move the decimal point 3 places, wouldn't it? So that would be 523.232323, etc. So now with these two numbers, let's call that one 1 and this one 2, I've got the thing after the decimal point is identical. So now I could just say, subtract those from each other, and on the left hand side I'll have 1000n minus 10n. And on the right hand side, 523 minus 5, because everything after the decimal place is identical, so that's just going to be subtracted out. So 523 minus 5 is 518. Therefore 990n equals 518. Therefore n equals 518 over 990, and that has, well, common factor of 2, doesn't it? So therefore n is equal to 259 over 495, and then that's in simplest form there. So I'm saying 0.523 recurring. Just be careful to show that the repetend only goes above the 2 and the 3, can be written as a rational number or a fraction, 259 over 495.